The center of pressure is a point where we can assume that the total sum of a pressure field is acting on a body. For example, if we have a dam, the water in the dam is exerting a pressure on the dam wall, and we might want to find the center of pressure of the dam wall, which is essentially the position where we can assume that all the pressure due to the water is acting on. This is very important in dam design, so pressure, calculating the center of pressure is very important in mechanical engineering design. As I have mentioned, in dam design, it is important. So in our case, we are required sometimes to find the depth of the center of pressure. For example, in the question that we have here, we have a triangular plate of sides 5 meters, 5 meters, and 6 meters, and it is placed vertically in a canal which is 5 meters deep. The longest side of the plate is horizontal and is 1 meter below the water level. It is very important in such questions for you to listen to the question so that you may be able to sketch what the question is saying, because without the right sketch, you cannot calculate this question, or you cannot determine the variables or the relationship between the variables x and y, or even calculate the second moment of area, which we need, by the way, if we're to find the depth of the center of pressure. So the first question says, sketch the plates and show the representative strip that you will use to calculate the area moment of the plate about the water level. So our calculation of the area moment of the plate is going to be about, so the reference will be the water level. Now I want to explain how you tackle this question, how you make the sketch, and the reasoning behind all the sketches. I'm going to explain just this example, but in all the questions, the approach is the same. First, you have to sketch what you're given, which is this area that you're given. You have to sketch it accurately. And then the second thing that you do from your sketch, you have to deduce or to determine a function that gives you the relation between x and y, these x and y variables. You are going to use that sketch to determine the relationship between x and y. Then after that, if you are to look for the depth of the center of pressure, you need to find the second moment of area of the plate, and also the first moment of area, or the area moment of the plate. The depth of the center of pressure is essentially, you find it by dividing the second moment of area of the plate by the area moment of the plate. In our case, we are given the area moment already. It is given as 28 cubic meters. That's the area moment we are given. So we just have to find the second moment of area. Then we divide the second moment of area by the area moment to get the depth of the center of pressure. Anyway, let us start with the sketch. I'm going to clear the board so that I can use a clear area. Now let's go to do the sketch. I'm going to use a different board. So here we go up. There we are. Now the sketch. We are told that this is a triangular plate, which means we have 3 sides and 5 meters, 5 meters, and the other one is 6 meters. And the 6 meter side is placed, the longest side of the plate is horizontal, which means the 6 centimeter side is horizontal, and it is 1 meter below the water level. Now, this drawing shall be on a Cartesian plane. I'm going to draw a Cartesian plane, and my reference point here is going to be the x-axis. So this is my x-axis, but let me use a different pen. So this is my x-axis. This is x, axis. My water level, I'm going to assume that my water level is the x-axis. This is my water level. So this is water level. This is the water level. Now the triangle has got 3 sides, and the longest side is 1 meter below. Now I'm going to draw also a vertical axis here, which is my y-axis in essence. So I'm going to draw my y-axis. I'm going to use a green pen again. So this is my y-axis, vertical. I'll label this y. I'm going to put some numbers on the y-axis. So if this is the origin, 0, so -1 is here. This is -1, where y is -1. It also happens to be the point where our triangle, the top of our triangle, which is the longest side, is situated. Let me draw that longest side. I'm going to use this ruler again. Okay, we're here. Let's position our ruler properly. I want to have a nice sketch. All right, now let me use a different pen. This is the longest side of our triangle, which is the top side, and they said it's 6 meters. I am placing this triangle such that the y-axis is bisecting it. It is cutting through the middle of this shape, which is what you should do always. Now from here, this is the triangle, by the way, and it is other sides. The other side is 5 meters and the other side is 5 meters. So both sides are here. I'm going to draw this side down. Okay. So this is my other side. Please note that this is a sketch. So this is the other side, and I will have the other side this side. So we essentially have what we call an isosceles triangle here. This is an isosceles triangle, so I'm going to draw the other side here. Now we have our full triangle. From the information that we're given, we need to find the coordinates of the vertices of this triangle, the coordinates of the vertices of the triangle. So this vertex here, remember we said this side here, this top side here, this top side, this one is 6 meters across. So it's from here to here is 3. So x here, which is the value of x at this point here, will be 3, and y is -1. So the vertex here has points 3, -1, and on the left hand side, this is the point -3, -1. So this is -3, -1, and this point here, which is the third vertex of our triangle, we know something. We know that x is 0. We know x is 0, but we don't know the value of y. Let's go back to our question. It may say something about this. They said the canal is 5 meters deep. The canal is 5 meters deep. So we measure the depth of the canal from the water level to the base here. So the water level is here where we have 0, which is the x-axis. And if we move 5 steps downwards, it means this point here is 0, -5. Y here will be -5. That is the depth of the canal. Now we have, this is the sketch of the triangle. The first part of the question, so we have sketched the triangle, and I'm happy with my sketch. The first part of the question says, sketch the plate and show the representative strip that you will use to calculate the area moment of the plate about the water level. So we want to calculate the area moment of the plate about the x-axis. We can make a horizontal strip here, which is, we can make a horizontal strip. That's what we should do. So let me draw this strip here. Let me use my ruler. So the strip will run from the throughout. It will run like it will be across this whole plate. So it's a strip, it's a thin strip. All right. This is our strip. Let me shade the strip. So this is the strip that we're going to use. So we are actually answering the question here. This is our strip that we're going to use. And the thickness of this strip is going to be dy. So the thickness of this strip is dy. Now with this sketch, we can now do question. Okay, the first part of the question says, sketch the plate and show the representative strip that you will use to calculate the area moment of the plate about the water level. If you do this, you will be given all the marks for doing that part of sketching the plate and showing the representative strip or about the water level. This is what you have done. Then they said, calculate the relation between variables x and y. Let me show you the question once again so that whatever we're talking about here, you can see it. This is the second part of the question here that says, calculate the relation between the variables x and y. That's what you have to do. I want to explain how you do that part. All right, let's go back to what we have. When you are here, the first thing that you need to do is to have these coordinates of the vertices. So you have this vertex and that vertex. You use this side. I'm going to use this side here, this side, to calculate the relationship between the variable x and y. So what we are essentially doing, we are finding the equation of the straight line, of this straight line here. We're finding the equation of the straight line, which is in the form y equals to mx plus sc. I want to say once more that if the shape of the canal is, let's say, a parabola, you are going to deduce or to find the equation of that parabola. If it is a straight line, you are going to find the equation of a straight line. If it is circular, you're going to find the equation of a circle. So in our case, we have a straight line. This side is a straight line. Someone may use this other side, but I prefer that you use this side here so that you work with a positive gradient. We use this right hand side, you're going to work with a positive gradient. Just find the equation of this straight line here, this straight line. We can find it because we have 2 points on the straight line. Once you have 2 points on a line, you are sorted. We also have something, we have C already. Let me start here. From here, we know C. C is the y-intercept, or it is the point where the curve is cutting the y-axis. It is -5. So we don't have to calculate our C. We are given the C. It's here on the graph. All we need, so we have C. All we need is to find M. Then half of the question, or the whole question will be done, by the way, because the equation of a straight line is simply y equals mx plus c. So M is the gradient. So let's find M. M is the change in y over the change in x. So it's -1. This -1 minus -5 minus -5 over 3 minus 0. If we punch in our calculator, we get M as 4/3. So it's 4/3. It's positive. It's a positive gradient. We expected that. Now, if we are to answer the first question, let me go back to the question. If we are to answer this question that says, calculate the relationship between variables x and y, then we are done. The relationship is a straight line, and we just want to show that straight line. So the straight line is y equals to 4/3x, 4/3x plus c, which is -5. So it's 4/3x minus 5. Done. We have done the first part of the question. This is the answer for the first part. This is the relationship between x, the variables x and y. We have it. Why do we need this relationship? We are going to need this relationship in calculating the other part of the question. Let me go back to the question once again. we have done this part. We have done this part. Okay. We have done this part. We have also done the second part. We are now worried about the third part. So the third part wants us to find the second moment of area of the plate about the water level, as well as the depth of the center of pressure on the plate if the area moment is given as numerically equals to 28 cubic meters. All right, so now let me have another board where I'm going to write this. So let's put this off. Let's come back here. All right, now we know that y is equal to 4 over 3 x minus 5. We know this. We know that the depth y bar, which is the depth of the center of pressure, y double bar I mean, is equals to y double bar is equals to second moment of area divided by the moment of area. Second moment of area divided by the moment of area. That is our y. And we are already given our moment of area, or our area moment as it is called. We already have it. All we need to find is the second moment of area. So we are finding here, so y bar is second moment of area divided by the moment of area. So second moment of area, second moment of area over moment of area, over moment of area. That's all you need to do. We already have the top part. We already have the bottom part. I mean, we need to find the second moment of area. We are going to rely on our strip once again. So let us go back to the strip so that I say something about the strip. The strip is the strip that we drew here. Let's put this off. The strip that we drew here is a horizontal strip with a thickness dy and the length of that, or the width, let's call it, actually the length of this strip. The length of the strip is going to be 2x. From here to there it's an x. We also have from here to there an x. So the length of this whole strip here is 2x. That is the length of the strip, 2x, and it has a width or a thickness dy. That's what we have. Let's go back to write the dA, which is the area of this strip. dA, the area of this strip. So dA, which represents the area of that strip. It's a small area, by the way. dA is 2x dy. This is dA, 2x dy. But we know something about the moment of area. Guys, if you know how to calculate moments, when we talk about the moment of a force, it is the force times a distance. Now, the same applies to the moment of an area. The moment of an area is the area times a distance. The second moment of area is the area times distance squared. The second moment of area is area times the distance. So if we are going to deal with this equation, we know that d is small ix. I is representing the second moment of area here. dix is equals to y squared, y being the distance of the strip from our reference axis, which is the x-axis, by the way. So this is y squared dA. This is it. Maybe I should point out why I am saying this. if you look at this strip of ours, this strip, the distance of the strip from the x-axis, this distance here, is a y. We call it a y because it's a vertical distance. We call it y. When we are calculating the second moment of area of the strip, it will be that distance squared times dA, which is the area of this strip. Please take note of that. It is very important. And I don't want to use in these questions, I don't want to use the formula. I just want to use the formula so that you see how it is happening. Now we know our dA. We know our dA here. Our dA is 2x dy. So let us substitute that. Let us substitute our dA. So we have here, this is equals to y squared times 2x dy. This is our dix. So this is the second moment of area of the strip, this thin strip. This is the second moment of area of the thin strip. So if you want the second moment of area of the whole triangle, we are going to integrate this whole thing here. So ix, in essence, ix will be equals to the integration from the bottom of the triangle, which is -5, to the top of the triangle, which is -1, y squared dot 2x dy. This is what we should do to find the second moment of area. We just have to do this integral. Now look for something here. Check here what we have. If we are integrating with respect to y, if we have dy here, you should make sure that your limits of integration, these two numbers here, are also y values. That is why I'm using -5 and -1. These are coming from my drawing. They're coming from this drawing, not from here. They're coming from this drawing here. I said this point here is x is minus. Okay, let me put this layer off. This point here has x is 0 and y is -5. And then the top point has y is -1. So y is -5 here, y is -1 on top. Remember, these are horizontal strips. So I'm adding all the horizontal strips on this triangle, all of them, from y is -5 to y is -1. That is what we mean by integration, because integration is essentially addition. So we are summing, we are adding up these strips. That's what we mean. I don't want to do many videos or many examples on this. I want to do one example, but explain it well, and you guys, you get it well once and for all. Okay, let's go back to where we were. Now, our limits of integration are fine. We are also happy that we are integrating with respect to y. This is fine. The problem is we cannot integrate with respect to y when we still have x here. We should find a way of eliminating this x and substituting it by a function that is only with y variables, with y as the variable. So we're going to rely on this. We're going to rely on our initial, on the relationship between x and y, by the way. So we can, from here, we can make x a subject of the formula, which is, it will be 3 over 4 times y plus 5. 3 over 4 times y plus 5. So y plus 5. This is what we have. So we can substitute x here by 3 over 4 y plus 5. We can do that. Now let us go to that step. So I'm going to clean the board, then I go to the next step. Now ix, which is our second moment of area, is equals to integration from -5 to -1 of y squared times 2 times 3 over 4 times y plus 5 dy. Now we have done something here. We now have y here as the only variable, and we are integrating with respect to y. This is what we need if we're going to do this integration. All right, now I'm going to inside this bracket, I'm just going to do some simplification. If I do that, 2 times 3 over 4, we get 3 over 2, which we can put outside here. 3 over 2 integration from minus 5 to minus 1. If I multiply by y squared inside the bracket, I get y cubed plus 5y squared. This is what I'm integrating with respect to y. Okay. Now we can do the integration once and for all. So we have 3 over 2. This will be y to the power 4 over 4 plus 5y to the power 3 over 3. We close here and we have minus 5 and minus 1. These are our limits of integration. So to finish off, this is definite integration. You substitute y equals to minus 4 into this function, and you subtract, after substituting y equals to minus 5 into the same formula. Then you punch in your calculator, you get an answer. That will be. So we are going to substitute minus 1 for y, then we substitute minus 5 for y, we get our answer. Okay, let me just write this. So this means we have here 3 over 2 times minus 1 to the power of 4 over 4 plus 5 minus 1 to the power of 3 over 3, all of this minus 3 over 2 times minus 5 to the power of 4 over 4 plus 5 minus 5 to the power of 3, all this over 3. This is what we have. We can just punch all of this in our calculator. Then we get our answer, which is the second moment of area. Let's punch that in our calculator. If you punch correctly into your calculator, your answer will be 76. So our answer here is 76. Let me write it in green. 76. The units are meter to the power 4. Meter to the power 4. The units for second moment of area, it's units to the power of 4. So this is our second moment of area, which is part of the question, by the way. Let me show you the question. I'm going to dim this question here. Calculate the second moment of area of the plate about the water level. So the water level in our sketch was the x-axis. That is why I used I subscript x. The second moment of area about the x-axis. That is what I did. We have it. We now have to calculate the center of depth, the depth of the center of pressure, I mean. To calculate the depth of the center of pressure, we divide our second moment of area by our moment of area. So the moment of area is given as 28. Our second moment of area, we calculated it as 76. So we can do the last part of the question. All right, let us go back to our calculation. This is where we were. Let us now find y double bar. Let's find y double bar. So this is y double bar. We said this is equals to the second moment of area. So second moment of area We divide the second moment of area by the moment of area. By the moment of area. Since this one is called the second moment of area, maybe the moment of area is the first moment of area. We divide the two. We were given this one. We calculated this one, so we just divide the two. So now we're going to divide 76 divided by 28. This is a depth, by the way. It will be in meters. So if we say 76 divided by 28, the answer is 2.714. 2.714 meters. I want to say something about this answer here and the moment of area. Even though we were told that our moment of area is numerically equal to 28 cubic meters. That is what we were told in our question. They are simply saying the magnitude of that is 28 meters. They didn't tell you the sign of the second moment of the moment of area. We're not told the sign. But because of our sketch, because our sketch was like this, where we had the x-axis and our area here was below the x-axis. Because of that, it means this moment of area here is going to be a negative value, because the distance y here is a negative distance. Y will be negative. That is why our moment of area should also be negative. Remember, the moment of area is the distance from the reference axis, in our case the x-axis, times the area itself. That is why it has to be a negative. Because this is negative, even our depth will also be negative. Remember, our reference level is the x-axis, which is the water level. So the depth is actually a negative depth. It's negative. I want to explain that you can also do the same question where you place the x-axis at the bottom of this triangle here. You place the x-axis at the bottom such that the triangle will be above the x-axis. You can do that. This is arbitrary, by the way. So you can do that and get away with it. The only difference now is that your moment of area will have a positive value, and your depth, or this value here, y double bar, will also have a positive value. So someone might ask, why is it that our second moment of area is positive? Our second moment of area is positive because it is r squared, the distance, times a. This is the second moment of area, r squared times a. So no matter the sign of your r, it is going to be squared. That is why in the end, this whole second moment of area will be a positive value always. It is going to be positive because there are no negative numbers in that formula. Whereas for the moment of area, it can be negative because the distance can be negative, or it can be below your reference point or to the left of your reference axis, whatever the case might be. All right, this is how you do this question. I can say here we have answered all the parts of the question. We did the sketch, which was the first question. We did the sketch here and we showed the strip. We also calculated the relationship between the variables x and y, which was essentially a straight line that we called y equals to 4 over 3 x minus 5. That is what we did. And we managed to calculate ix, which was the second moment of area. We calculated it. We were given already the area moment, or the first moment of area. We had it. We also had to calculate the depth, which is y double bar, the depth of this. We had to calculate it. We found it because we find it by dividing the second moment of area by the moment of area. This is how you do this question. I just want to highlight one more thing before I end the video. Because in the exam, you may have to rely on your formula. You are going to find a formula that you need, the formulae. that you need for center of pressure, questions, you are going to rely on the formula for y double bar. This y double bar, you may find it as integration of r squared dA over integration of r dA. You may find the formula like this. If you know your formula very well, you will find that this formula here is the formula for the second moment of area. This is for the second moment of area, which is usually represented as Ix or Iy, etc., depending on the convention being used on your formula sheet, but it is essentially the second moment of area. The formula below is for the area moment. So this is for the moment of area. Moment of area. That is the formula for the moment of area. It can be AMO, area moment, Y, or AMO, X. Depending on what we calculated in our example was, or what we were given was AMO X, the area moment, the moment of area with respect to the x-axis, or sometimes you may have to calculate the moment of area with respect to the y-axis. It depends on the question that you're given, but this formula here below is for the moment of area. So you'll find it there. Everything is given. All you need to know is that y double bar, the depth of the center of pressure, is given by dividing the second moment of area by the moment of area. How to calculate the moment of area is a subject for another video. How to calculate the second moment of area is a subject for another video. But in this video, I explained all the concept from calculating the second moment of area, making the sketch, calculating the center of pressure by doing the division. Otherwise, thank you for watching the video. Give it a thumbs up and share with your friends. Don't forget to subscribe to the channel. Thank you.